Hello friends, welcome to the course Exploratory Data Analysis for Data Science with R Software. You can recall that in the last lecture we initiated a discussion on the variation in data, and we wanted to develop different types of statistical tool which can measure the variability in the data. And then we use the concept of maximum values, minimum values, and different types of quantiles, say quartiles actually, first quartile and third quartile, to develop different types of statistical measure to measure the variation. Now, in this lecture, we will continue with the same topic, and we would like to develop some more measures of variation. And my objective here is not to tell you about these measures. They are already available in the books. My idea is that I want to give you the thought process, that how they have been thought and what is the feature of the data which they are trying to use to give us a value which is depicting the measure of variability inside the data. The reason being, when we are working in the data science, which is relatively a new area, means in the sense statistics is much older. So there are many situations which are strange and for which the solutions have not been really addressed in statistics. So under this type of situation, you may require to develop some new tool. And when we are trying to work with the computation, writing a program is much simpler than doing the algebra. So that is why you can compute it. But what does these computations are going to give you? This is very important to understand. And this will open a new area for you, that you can develop new types of this statistical measure for measuring different types of characteristics in the data. So that is why in this lecture I will try to take up the concept of deviations. The deviation of the data from the central value or any other value inside the data. And then I will try to develop here a measure of variation. And in this context, I am going to use here the concept of absolute deviation and square deviation. And in this lecture, we are going to develop a statistical tool based on the concept of this absolute deviations, and I would develop here the absolute mean deviation. And in the next lecture, I will consider the squared deviation. So let us begin our lecture and see how we can develop these concepts, these tools, and how we can implement them in the R software. Okay, so let us begin our lecture. You had seen in the last lecture that we had talked about the range, interquartile range, quartile deviation, which were based on specific values and partitioning value. Now we want to develop here a new measure based on the concept of deviations. And if you try to see, the issue with the earlier methods like as range, interquartile range, quartile deviation, etc., was that they were based on specific values. They were not based on the values of all the sets of data. So definitely in statistics, we have a basic concept. If you use more data, then you get better information. That's the rule of thumb. So we would like to develop here a measure which is using the entire data set to give us a value of this variation. So if you try to understand, first let us try to understand what are we trying to do. Suppose I have here some data. I'm just making here only a couple of points so that I can show you here clearly. Now, suppose this is your here data. You can very easily see that this data is contained somewhere in this type of area. Now, when I want to seek the variability of this data, then first of all, I have to define the variability with respect to which point. This data point can be anywhere. For example, this data point can be here also, or here also. So I will not consider these two data points, but I will consider here this data point. So, black color point is the point around which we would like to see the variation of data. So, if you try to see here from this point, the variation here is like this for each of this data point, like this. And now the next question is, how are you going to measure it? Suppose if I try to make it here a line, and suppose if I say this is something like my say axis, x and y axis, and it is here my 0, 0 point. Now, if I say here, this is my suppose here point here A, and now in case if I try to measure these deviations on the left hand side and right hand side of this blue line. So, what will happen here? Suppose if I say this is my here point number 1, this is here the deviation say D1, and similarly for the point number here 2, which is here like this deviation here is D2, the difference between A and this point. And similarly here point number 3, the deviation here is D3, point number 4, the deviation here is D4, point number 5, the deviation here is D5, point number 6, and the deviation here is D6. So, now if you try to consider the two aspects, the magnitude and the correction of this deviation. So, for the magnitude, you can see any point who is more away from the center point will have more magnitude of the deviation, right. For example, this point number 4 has more deviation than the point number 6 in terms of magnitude, right. But then we also want to measure here the variation, the correction of this variation with respect to the point A. So, you can see here very clearly that in this case the variation on the in this area, this can be taken as say negative. So, D1, D2 and D3, they are negative in the sense that they are trying to measure the difference between xi and A. So, this is on the negative side. And similarly, these points say here point number 4, 5 and 6, here this D4, D5 and D6, they are greater than 0 because in this case the value of xi minus A is greater than 0, right. So, now in case if you try to consider all these deviations or you want to consider all the data points to contribute in developing a measure, then one option is that I can take the arithmetic mean of this 6 data points, I goes from 1 to 6 di. But now the problem will be that some of the di's are positive and some of the di's are negative. So, it may happen that this value may come out to be 0 or very close to 0, and ideally what you can say, there may be some di's which are exactly lying on the line. So, or on the point A they will be exactly 0. So, now if I say there is no variation in the data, then it is a wrong statement. So, now if you try to see when we are trying to develop this variation measure, where is the problem? The problem is lying with the di's and its sign, that some di's are negative, some di's are positive, which is creating this trouble that we are not getting a proper interpretation of this, of the value of this measure. So, one option is this, we can make this measure based on di's which are independent of the sign plus or minuses. So, I have here two options. If I want to make this di's independent of signs, then I have two options. I can consider here the absolute value of di's, or I can consider here the squared value of di's. So, taking absolute or making them a square will make all the values to be greater than 0 positive, and based on that we can think about that how we can develop a proper measure. So, for example, one option can be we can take the arithmetic mean of all the absolute values of di's, or another option can be we can take the arithmetic mean of all the values of squared di's. So, in this case there won't be an issue of the signs of di and possibly we will get some measure. So today in this lecture, we are going to consider the concept of this absolute deviation, and in the next lecture we will consider the concept of this square deviation, and we will try to develop here the statistical tool which are going to measure the deviation, right? Okay, so now as I told you here, as I explained you, now I can tell you that whenever we are trying to measure the deviation of any observation xi from any value a, then I can define the deviation here as a di is equal to xi minus a, as I did it. Now, in case if xi is greater than a, then such deviations are positive. If xi is less than a, then such deviation di's are negative, and if xi equal to a, then such deviation di's are 0, right? So in case if you try to find out here the sum of 1 upon n I goes from upon 1 to n di, then there is a possibility that this average value may come out to be very close to 0, indicating that the data has very less variability, which may not be true, right? So that's what I'm trying to say here, that if we consider the average of such deviations by here 1 upon n summation di, this value may be close to 0, and it will reflect that there is no variation or very small variation in the data, which may not be correct. So that means we do not want to consider the signs of these deviations. We need to consider only the magnitude of the deviation, and based on that we will try to develop here the tools based on two concepts. Consider the absolute value of this deviation or consider the squared values of these deviations, right? And now we will try to develop in this lecture the statistical measures for based on the absolute value of this deviation, and in the next lecture I will consider the squared values of these deviations, right? And because now we have considered here two types of data, say ungrouped data and grouped data, so we will try to develop these tools for both the case. At least from the fundamental point of view, you should know how these tools have been developed. After that, it is your choice which of the tool you want to use depending on any situation, right? So suppose if I consider, firstly let me try to give you the symbols and notation for this grouped and ungrouped data, so that later on I can just concentrate on the development of the tool. So if my data is ungrouped, then I will have a random variable or a variable capital X, and on which we have obtained the data as small x1, small x2, small xn. For example, if x is the height, then there can be 20 values of the heights of the students in a class, like as 140 centimeter, 150 centimeter, and so on. So these are your lowercase x1, x2, xn, right? And in case if we are considering the random variable x to be continuous, then in that case we have got the data, and that data x1 has been tabulated into k class intervals in the form of a frequency table. And then the frequency tables are here like this, that we try to find out here the class intervals, and then we try to find out their midpoints, say xi, something like here x1 will be e1 plus e2 divided by 2. And then we try to find out the frequencies, that how many values are lying in the interval e1 to e2, right? So this x1 is occurring with frequency f1, x2 is occurring with frequency f2, and so on, and f1 plus f2 plus fk is equal to here small n. That is my symbolic notation which I will be using. Right, now if you try to see, first I try to define the absolute deviation of observations x1, x2, xn around a value a, some arbitrary value. I am not saying it is mean, median or something else. So now what I try to do, I consider the deviations d1, d2, dn. I try to find out their absolute values so that they become independent of the sign, and then I try to find out the arithmetic mean of this deviations. I goes from 1 to n, one absolute value of di and divided by n. So this is what I am writing here, 1 upon n summation I goes from 1 to small n and absolute value of xi minus a. So this is for the discrete data or say ungrouped data, and you can recall that when we developed the arithmetic mean for grouped and ungrouped data, we had used a similar definition and similar methodology. So the same thing I am using here once again. So now in case if you consider the data to be grouped or say from a continuous variable, then you can recall that we had defined the arithmetic mean x bar as say 1 upon n summation fi xi, and summation was over all the class interval. So using the same analogy, I define here the absolute deviation like 1 upon n I goes from here 1 to k fi and absolute value of xi minus a. But now here n here is this total frequency. I goes from 1 to k fi. So you have to be careful while using these symbols and notations. Right. So these are called here as a absolute deviation. Right. And now if you try to see here, I am using here a value here a, and I am trying to measure the deviation around a value a. Right. So now the next question is that what should be the value of a around which these deviations will take the minimum values. So if you try to do some algebra, very simple algebra, then you can find out that this absolute deviation of observation x1, x2, xn is going to achieve the minimum value when it is measured around the median. That is, capital A is the median of the data. So if I try to replace capital A by the median of the data, for example, here if I say here this A is now my here median, and similarly A here is the median. The only thing is this, you have to see how you want to calculate the median based on group or ungrouped data. Then this absolute deviation is then termed as absolute mean deviation, and it is defined as, say here 1 upon n summation I goes from 1 to n absolute value of xi minus x bar median for the ungrouped data or for the discrete data, and it is defined as 1 upon n summation I goes from 1 to k fi absolute value of xi minus x bar median for continuous or the group data where your small n is the sum of all the frequencies. So this is the definition of absolute deviation and absolute mean deviation, right? So both this absolute deviation and absolute mean deviation, they are measuring the scatteredness of the data around the value A and around the value median of the data respectively. So absolute mean deviation measures the spread and scatter of data preferably around the mean value in terms of absolute deviations, right? Now, how are you going to make the decision making? So if so the rule is very simple. As earlier, we will try to compute the either the absolute deviation or the absolute mean deviation, whatever you want, and then the data set having a higher value of either absolute mean deviation or equivalently absolute deviation is said to have more variability. And so if you have two data set, then you have to compute either the absolute deviation of both data set around the point A, or you try to compute the absolute mean deviation which is around the medium of the data set, and try to see whose values is coming out to be lower. The data set with a lower value of absolute mean deviation or equivalently the absolute deviation is preferable. And so if we have two data sets and suppose we compute their absolute mean deviation, or say here say AMD1 or and AMD2, and if AMD1 is greater than AMD2, that means data in the AMD1 is said to have more variability than the data in the AMD2, right? So now the next question comes over here, that how are we going to compute it in the R software? So I can share with you that there is no direct command in R to compute these values. But on the other hand, writing a statement to compute this value is also not difficult at all. If you try to see, if I am writing this definition for ungrouped data, this is here absolute value of xi minus a, and then you have to take its sum and then divided by the total number of observations. So if you try to see, this is not something like arithmetic mean of the values xi minus a, right? So in case if you want to write down the data vector for xi minus a, can't we write it here as x minus a? And after that, what you have to do? You have to take its absolute value. So let me try to write down here absolute ABS function. And then after that, what you have to do? You have to take the arithmetic mean. So I can write down here the mean of absolute value of x minus a. That's all. So this is how I can compute the absolute deviation for a given value of a by this command mean of absolute of x minus a. And in case if I want to compute the absolute mean deviation, then I know in case of ungrouped data, I can very easily compute the median by using the command median, median of x. So I replace a by here median of x, and my absolute mean deviation can be computed by mean of absolute value of x minus median. Right. You have to be careful when you are trying to consider the group data, then median has to be calculated separately. Now, in the same case, if x data has got some missing values and we denote them by capital NA and the data is stored in a data vector here XNA, then the R command becomes mean of ABS inside parenthesis the data vector x and a minus a, but now you have to use here the command na.rm is equal to true. And similar is the story when you try to find the absolute mean deviation, that you have to use the same command, but you have to replace a by here median, and the median will also be computed by removing the missing value. So median xna comma na.rm is equal to true, right. So now if I consider the group data, then you can recall from the past that in the case of group data we need to have two data vectors, here x and here f. X is the data vector of the midpoints of the class intervals and f is the data vector of the absolute frequencies, right. Now, in case if you try to see what is your definition, 1 upon summation fi I goes from 1 to k, and then summation I goes from 1 to k, say fi and absolute value of xi minus a. So this xi minus a can be written here as say x minus a. Then you are trying to find out its absolute value. So I can use here the function, say this abs, and then you have to multiply it by here fi. So it will be multiplied by the data vector here f, and then you have to find out its here sum. To find out summation I goes from 1 to k, and then you have to divide it by here sum of the data vector here f, right. So this is the same expression which I am giving here. So you can see here for a given value of a, you can very easily compute this statement. And similarly, if you want to find out the absolute mean deviation, then this a will be replaced only by the median of the data x. But in this case, you have to be careful that the median in the case of group data is not going to be used by the command median, median, but it has to be tabulated and then the median is going to be computed. Although in data science, I agree that there may not be much difference between the two commands as I told you earlier, but here at least as per the rule, you have to compute the median separately using those commands. So I can use this median which is computed separately for this group data vector, and then I will replace it, and this command sum of f into absolute value of x minus x median divided by sum of f will give us the value of absolute mean deviation, right. Okay, now let me try to take here an example and try to show you how I can compute these things, right. So let me try to take here the same data set where 20 participants participated in a race, and their time to complete the race in seconds is recorded here, and this data is going to be recorded as here time, time. Right. Now, suppose if I say arbitrarily I choose any value here capital A to be here 10, and I want to measure this absolute deviation around a equal to 10. So then I use here the same command and mean of absolute value of time minus a, and then this comes out to be here 46. And in case if you want to find out the absolute mean deviation, then I can find out here the median of time that you can see here, this is 56.5, and then you use here this median of time here. So then you get here this absolute mean deviation as 14.5. So you can see here 14.5 is much smaller than 46, because as per the rule, as per the principles of statistics, this absolute deviation is going to give us the minimum value when it is measured around the median, right. And this is here the screenshot of the same operation. Now I consider the same data as the group data, and I try to create here a frequency table. So the entire data has been divided into different this class interval 31 to 40, 41 to 50, 51 to 60 and so on. And then we have obtained their midpoints like as 31 plus 40 divided by 2, which is 35.5, and other midpoints. Then we have counted the absolute frequency, that there are 5 values which are in the interval of 31 to 40. There are 3 values which are in the interval of 41 to 50, and so on, right. So now our objective is this: we need to find out the frequency vector f and median, right. X values are already obtained here in this column here, right. So now I will not go into much detail, but I already have used this concept several times by using the command breaks and haircut. So what I try to do here, in order to obtain the frequencies, I try to create here a sequence from 30 to 90 at an interval of 10 integer, which is denoting the width. So I create here a sequence from 30 to 90 by 10, and then I save them in the command here breaks, right. And then I try to use the command here cut, so that I can convert this data into a factored data where I can use the command table, right. So I use the command here cut over the time with using breaks and right equal to false to indicate that the the intervals are open on the right hand side, and this data is saved here in time.cut. So you can see here that these 3 data values which are here, actually see here 32, 35, 45, which are indicating here that 32 is here, 35 is here, 45 is here, and so on, right. So now I try to use this table command over this time.cut, and I get here this frequency table. So there are 5 values in the interval of 30 to 40, 3 values in the interval of 40 to 50, and so on. And I want to extract these absolute frequencies from this outcome. So I use here the command as.numeric and table of time.cut, and I get here this frequency vector here f. So I simply try to use here the data vector of midpoints x, which I have obtained earlier, and then I have obtained that breaks and cut command to obtain here the values of here, say here f. And then now from these intervals we have to find out the median class. So the median class is obtained here as the third interval, above and below which there are 50% observation. So in this case m is equal to 3, and this is my class interval. The lower limit of the class interval is 50. The frequency of the medium class is 3 by 20. Width of the median class is 10. So I can use here the formula that we had discussed earlier to obtain the median. In such a case, I substitute all the values and I get here 56.66, right. Now I try to take here this frequency vector here, this f, the x data vector of the midpoints, and I use here x median here as a 56.66, which I have obtained here actually, right. And now, and earlier this a was actually 10, that is what we had used. So if you try to see here, in this case, if you try to find out the absolute deviation around the point A, then it is coming out to be 46. Whereas if you try to replace A by the x median, then this absolute mean deviation around median is coming out to be 14.166. So you can see here it is much smaller than the value 46, and the same thing happened in the ungrouped data also, right. And now if you try to see in the ungrouped data, this value came out to be 14.5 when you consider the data as a ungrouped data. And now when you are trying to consider this data as a group data, this is 14.16. So there is not much difference between the two values, right. So now if you try to see here, I just want to show you here the comparison. When you take this mean, this absolute deviation around a equal to 10, value was 46, and in this case also group data also the values are here 46, they are the same. And in case of group data, when you compute the median using this frequency table, then this value here is 14.16, and earlier when you consider the median command directly over the ungrouped data, then it was 14.5. So you can see here that is not much difference. And when you try to go for some bigger data set, as in the case of this data science, then these values will have much lower difference, and that difference may not be significant. So now let me try to show you that how are you going to obtain these values in the R software. So let me try to have this data over this here time, and suppose if I take here a equal to here 10, right. So now if you try to see here that I can find out mean of this absolute value. In this case, this is here, see here, around a value, it is here 46. And when I try to consider this thing around this median, then this value here is like here 14.5, right? And similarly, if you try to do here all these things, yes, these things we already have obtained. So if you try to take here these values here, so f here is say like this, which you have obtained. Yes, we already have done this exercise couple of times earlier. And this x data vector, which is the data vector of the midpoints, and x median here, what you have obtained say manually, this is here 56.66. And then if you try to obtain this absolute deviation, then it is coming out to be here like as 46. And if you try to obtain here the, see here, this absolute deviation based on the mean, that is absolute mean deviation, then this value is coming out to be here 14.166. So you can see here it's not a very difficult thing to obtain this thing, but the more important part is that which of the tools should you use. So as I told you earlier also, that when we are taking such a small sample, then you have seen that using this absolute mean deviation and absolute deviation, the numerical values are coming out to be there. They have some difference, but the difference is not that high. And I believe that when you are working on bigger data sets where the variables are continuous and the data is flowing continuously, which happens in the data science usually, then there will not be much difference in the values obtained by both the methods, whether you consider the data as group data or say ungrouped data. So, and you will not get much different results. So, you can safely use any of the method, whatever you want. Now, in the last, I can give you an example where that how are you going to compute this thing when you have the missing data. So, now I take the same example where first two observations on the time of the race are missing. They are indicated by here NA. So, I write here NA and NA and I stored this data time.NA. where now we have here 18 observations. And then now this is my here data time.NA, A is equal to here 10. And then I try to compute here this, the absolute deviation from this missing data, it comes out to be 48.5. Then I try to use the median and I try to use this absolute mean deviation, which comes out to be here 61.5. And based on that, I try to replace this thing and I try to compute this absolute mean deviation based on this median. So, this comes out to be 13.38, which is again much smaller than the absolute deviation. And this is here the screenshot you can see here, but I can show you these things on the R console also. So, let me try to save this data here. So, this is my here time.NA data, and then A already I have taken to be 10. I can type here once again here A equal to 10 so that it is clear to you. Then I give here this command and I obtain here the mean, the absolute deviation, and when I try to obtain this here absolute mean deviation by computing the median, then it is coming out to be 13.38. So, you can see here it's not a very difficult thing to obtain. Right. So, now I will stop at this lecture and you can see that what I have done. I have introduced here the concept of deviations, the deviation of individual data point from certain value. And based on that, we have developed a measure to find the value of the variation in the data. In this lecture, we have considered the averages of such deviation based on the concept of absolute value. And in the next lecture, I will try to consider the squared value of the deviation and we will develop similar type of these measures. Well, these are based on different concepts, right? And for example, you will see that when we consider the squared deviation, then there we are going to use the arithmetic mean in place of median, what you have used in this lecture. You have measured the absolute deviation around median and you said it is going to give us the minimum value, but in the case of square deviation, it will give you the minimum value around the arithmetic mean. So now these are different concepts. So you know that if your data has got some extreme observation, then median is not that much affected, whereas the arithmetic mean gets affected very easily. So now you have to see that given the data set, whether it has extreme observation or not, etc., then you have to see which of the tool is going to give you the real picture of the variation inside the data. And my recommendation is that whenever you are trying to deal with the real data where you have no clue what is happening inside the data, so better is to use all such tools. It just take a couple of seconds to execute them on the R software to get their values, to create different types of graphics, and try to see where you are going, where you are successful to match the information which is obtained from the analytical tools and the graphical tool. That will give you more confidence. So I will request you now that please try to take some small data sets in the beginning and then try to find out their absolute deviation, absolute mean deviation, and try to change some values, try to add some extreme values, lower values, etc., and try to see how the values of this absolute mean is changing. In the next lecture, after we discuss the concept of variance, which is based on the square deviations, then I would ask you to compare with absolute mean deviation. And then you try to take a bigger data set and see, are you successful in finding out the information hidden inside the data? So you try to practice it, and I will see you in the next lecture. Till then, goodbye.